Welcome to the Water Resources Podcast. I'm your host, Bridget Scanlon, from the Bureau of Economic Geology at the University of Texas at Austin. This podcast is produced in partnership with the National Academy of Engineering. In this podcast, we discuss water challenges with leading experts.
Thank you, Michelle, for joining us. Today, our guest is Michelle van Vliet, who is a professor at the Department of Physical Geography at Utrecht University. And appreciate your joining me for the Water Resources Podcast.
Yeah, thank you very much, Bridget, for inviting me. Very nice to join your podcast here.
And Michelle's work focuses on global change impacts and adaptation in relation to water resources availability and water quality for sectoral water uses, including irrigation, domestic and energy uses, and considering ecosystem services. So today we would like to focus on your recent work on regional and global surface water quality and how water quality affects water scarcity, because most people focus on just water quantity issues. And then describe a little bit about the tools that you use to assess water quantity and quality, modeling tools, data analytics. And then lastly, but not least, is the potential solutions to these issues with your work on wastewater reuse and desalination. So first, I guess, Michelle, let's talk about some of the recent research that focuses on water quality. And we've heard quite a bit in the news about water quality issues in the Netherlands and surrounding countries. And maybe you can describe that. I know you haven't focused on the regional aspects, but it would be good to hear your take on what we've been hearing on the news about those issues.
Yeah, sure. And thanks for asking. Yeah, you're right that indeed in the Netherlands and also some surrounding countries that we are currently facing challenges in terms of meeting these European water quality targets as specified by the European Water Framework Directive, and also in terms of specifically meeting the nitrogen targets for nature development. So last year, our government announced some major transitions for agriculture to keep below the nitrogen thresholds for nature restoration. But indeed also, farmers are quite unsatisfied with that set of, and also with those announcements. So that actually, resulted in quite some aspects also in the international media. Also, what I understood, indeed, angry farmers blocking highways, indeed. So we are actually currently facing certain what is called a nitrogen crisis, but that could potentially also move into more an overall water quality crisis, because not only nitrogen is an issue, but we are actually scoring in terms of water quality status, and the percentage of waters that are of good quality overall rather low, and we need to officially meet the targets of the European Water Framework Directive in 2027. So it will be quite challenging actually to meet those targets by then. And so that's actually one of the challenges that we are facing, indeed, specifically in the Netherlands, where we quite intensively use our land and water system due to quite high population density, a lot of intensive agriculture industries. But also urban traffic that all contribute to water pollution. So that's actually quite an important aspect, which is also indeed widely reported also in the national media, but what I understood indeed also in the international media.
Right. So in the US, and I know you spent some time in graduate school in the US, I think you did one of your degrees there. We have the Clean Water Act and the Safe Drinking Water Act. And in Europe, you have the Water Framework Directive that was passed in, I think, the year 2000. And that act, then you're supposed to ensure good quality water of sufficient quantity for humans and wildlife. And that includes quality and quantity of groundwater and surface water. Maybe you can describe that a little bit, Michelle, and the different good, moderate, or poor, or how they, what they discuss, and what the deadlines are and you get exemptions then. And so you mentioned 2027 that you're supposed to meet these deadlines, but you've missed deadlines in the past, I guess, and then there's a lot of pressure. I mean, you have a wet climate, you have a shallow water table, you have sandy soils that let a lot of this go into the groundwater. So, and then the groundwater discharges to the surface water, so it's all connected.
Yeah, it's all connected, like you say, and indeed we officially need to meet now these European water quality targets in line with the European Water Framework Directive in 2027, and that is really the last deadline that is provided, because actually 12 years ago in 2015 actually we had to meet already those targets, but this was postponed actually twice 6 years. I mentioned already the issue of the nutrients, but indeed, actually, it's more, and we look at much more water quality constituents also with the European Water Framework Directive. So the nutrients are one of them, but indeed also high concentrations of heavy metals are a concern. But we also see pop-up of new chemicals, or relatively new chemicals, which do not naturally exist in our waters, like for instance PFAS. Microplastics, also pharmaceuticals, because some of them are also quite hard to remove also by wastewater treatment. So this is not only in terms of water of good quality that is needed for nature, but this is also actually for many water users, including drinking water. So also drinking water companies, so in our country, in the Netherlands, are indeed already concerned about this development, because indeed some of these chemicals are really hard to remove, and like indeed some very persistent pharmaceuticals, for instance. What we also have seen in our research, also in my group, we also looked, for instance, at the impacts of droughts also on concentration of pharmaceuticals in quite a number of rivers in Europe. And there we see also indeed increased concentrations, but and specifically under droughts, because there's also less water available to dilute, so that also increases concentration. So also increases in droughts in both the frequency, the intensity of droughts will also not help in that way. So this makes this urgency even more in terms of improving the status of water quality.
Well, I mean, it's good that you have these regulations and the Water Framework Directive to help guide some of these things. And I was listening to another podcast, and they said there has been improvements in nitrogen and phosphorus, and with half of the waters now meeting the directives for those nutrients. And you mentioned emerging contaminants, and we're also dealing with that with PFAS and other things. And I guess when you say persistent chemicals, I mean, I think they use the term forever chemicals for PFAS, and so very difficult to treat.
Exactly.
And the other issue that you mentioned, we've always had the mantra in the past is dilution is the solution to pollution. But when you have droughts, then you can't rely on that. And
exactly.
So it's many things coming together. We can measure these chemicals at much lower levels now, and so we're becoming more aware of these things, and so it's continually evolving. And we will also be trying to address. We are also trying to address these issues, emerging contaminants in the US and other regions. Maybe I would like now to talk a little bit about the tools that you use to evaluate surface water quality. And you have done global analysis on surface water quality using modeling tools like DIN-QuAL. And maybe you can describe that and what you can do with those modeling tools.
Yes. We have indeed in my group developed some data-driven modeling tools, but also more process-based water quality models, including indeed the DIN-QuAL model that we recently developed. And so that's mainly developed with the aim to study water quality trends and hotspots across the world. And in terms of data-driven models, we mainly built on machine learning techniques, using, for instance, random forest in terms of identifying drivers that contributed to certain water quality trends, but also building on a large number of water quality monitoring data, using this with machine learning techniques also to show more the spatial explicit hotspot regions in the world. So we actually build on both techniques, both data-driven reported data, but also using more process-based water quality modeling. And that process-based water quality modeling we also use for scenario analysis, like including studying impacts of climate change and socioeconomic developments on surface water quality. And so there we...
Oh, go ahead, sorry. I mean, I think your DIN qual builds on, I mean, people oftentimes may not consider temperature as a water quality parameter, but your DIN qual process modeling leverages off of your original work looking at temperature. Is that correct?
Yes, we used indeed different temperature models indeed for that as basis, and building here indeed on the DIN watt temperature model that has been developed in our group by Rens van Beek and my colleague Nico Wanders. Also the water temperature modeling that I did myself, more as part of the RBM model framework, which actually has developed in the US. With John Yearsley, for instance, and others from University of Washington. So we started actually, and it was also when I started with my PhD project, we started to focus on water temperature modeling. And now we have also expanded this to include more water quality constituents, so focusing on salinity, organic pollution, pathogen pollution. And actually also some new PhD students that recently started will also look at other water quality constituents. So we actually are further developing this approach.
So DIN qual, maybe it's an older paper that I'm looking at, but it seems to focus on temperature, biological oxygen demand, and fecal coliform. And are you now expanding that to consider other parameters? But your machine learning approaches, are you focusing on data over the past couple of decades? Addresses more parameters, maybe. Is that correct? Like nitrate and pH and phosphorus and other parameters?
Yes, that's indeed correct. So with this data-driven approach, so this is also work that we did actually in collaboration with the World Bank. The World Bank led actually this study in terms of using machine learning approaches for mapping global water quality hotspots. And so they used random forest techniques and used indeed data of water temperature, pH, dissolved oxygen,
and nutrients.
Nitrate, nitrite. So those were indeed considered as part of that. So also quite a number of water quality constituents that are indeed relevant for this SDG indicator on good ambient water quality.
Right, Sustainable Development Goals, right, SDG, and I guess it's SDG 6.3.2. For good ambient quality water bodies, and SDG 6.6, I guess, which addresses ecosystem services. In some of your global analysis, you characterize the pollutants as pollutants of poverty and pollutants of prosperity. And I think that's a really nice way of thinking about it, because we may think that prosperous or developed nations may have better water quality, but actually they just have different water quality issues, it seems. Maybe you could describe that a little bit, Michelle.
No, thanks for asking. That is indeed exactly what you say, and we see that poor water quality, that is not indeed only the issue in low income countries, but also indeed middle and high income countries, but with different pollutants. And so we overall see that when countries actually become richer, that water pollution does not disappear, but it evolves. And so we consider some pollutants of poverty, which are mainly due to poor sanitation or actually complete lack or very limited wastewater treatment. And so in those areas, we commonly see high concentrations of organic pollution, pathogen pollution, for instance, indicated by, for instance, fecal coliform. But we also see some pollutants of prosperity related to intense economic activities. So those are mainly the pesticides, microplastics, pharmaceuticals, to some extent also nutrients. And some of these, like we discussed already, are quite hard to remove by wastewater treatments. And so we see actually indeed that that water pollution actually evolves in that way if you when countries become richer.
Right. And, when you do the global analysis, then you can identify hotspots of water quality issues. And where do you see, I mean, it seems that we would think obviously of US and all the manufacturing and development and things like that, but where do you see the hotspots globally, or where do you think the biggest issues are?
Yeah, we look at, for instance, salinity and organic pollution in fecal coliform. So those are the water quality constituents that we capture together with water temperature as part of the DINQUAL model, so the process-based water quality model. And there we see the main hotspots mainly in Eastern Asia, and mainly Eastern China, India. So if we look at nutrients, this is indeed also Europe, like Western Europe, particularly the Netherlands, like we discussed already, is also facing issues there. Also parts of the US. So it depends also a bit on the water quality constituents that we consider. But those can be considered as major hotspot regions indeed.
And so when you talk about pollutants of poverty, I guess they would be found mostly in developing countries, and they may not be highly concentrated and may not show up so much in your global maps, but be more localized maybe, or even in urban areas, you might have hotspots. Because fecal coliform and DO issues in urban settings in developing countries, maybe Africa, sub-Saharan Africa, and those regions, and parts of India. So it kind of emphasizes that it would be great if we could treat the wastewater and then reuse that, and then also that would have multiple benefits of reducing water quality issues in those regions.
Yes, that's correct indeed. That's quite important to work on to improve water quality. So we should definitely focus on that. Actually, also as part of a study that we did in our group, so this was based on the work of the PhD project of Edward Jones, we actually also looked into what would mean if we would consider an SDG 6.3 target, which focuses on halving the proportion of untreated wastewater in the world, so by expanding wastewater treatment. But here we also indeed identified that this results indeed in distinct improvements in surface water quality. But particularly in developing countries, we found that this was actually insufficient to improve the water quality in a way that the concentrations remain below the key water quality thresholds. And so more is needed there actually in terms of emission control measures. And you also mentioned Africa, which is indeed a very interesting region also. Given the developments going on there, also the socio-economic developments, the huge population growth. And we also started recently to look also into the impacts of socio-economic developments, looking at population growth, but also looking at projections of wastewater treatments that were made also by an integrated assessment model, and look into what the impacts are on water quality, and combined also with climate change, where we already also discussed changes in, for instance, droughts, and actually the flow patterns in general will affect also the dilution for pollutants. So those are important developments, and there we see that particularly the global south and specifically Africa will indeed become a major critical region in terms of water quality development, so a major hotspot in that sense.
Yeah, we normally think of population growth and hotspots of population growth being China and India, but Africa is going to be the future, and so that's going to be more and more critical, I think. I really like your analysis of temporal variations in water quality. Also, you've looked at data over the past couple of decades, from the early 90s to 2010, and looking at changes in temperature and dissolved oxygen and nutrients in different regions. Maybe you could describe that a little bit, Michelle.
Yeah, sure. In terms of these more these long-term trends, we see that based on this study that we did together with the World Bank. We used indeed a data-driven approach. So we used random forest, and we did some trend analysis also next to that to look into regions of the world that show a deterioration in water quality or improvements. And so there we found actually that for about 30% of the global land surface area that we found a significant deterioration in water quality over this period of 1990 till 2010. And 22% we found an overall improvement. We discussed already a bit in terms of this the deterioration of water quality, that this is particularly strong in the global south. Actually, that is when we look at the trends from 1990 till 2010, so these historical trends, but also when we are going to extrapolate these, or when we use process-based models actually to develop projections of surface water quality under future developments, focusing on climate change, but also socioeconomic developments. So there we indeed also see major deteriorations, particularly in parts of the global south, particularly Africa.
Right. And most people, when they talk about water scarcity globally or regionally, they focus on water quantity issues. But in your global analysis, then, when you consider water quality along with water quantity scarcity issues, you see that the population impacted increases from maybe 30% to 40% of the population impacted by water scarcity, if we include water quality. I think more people will need to do that in the future and not just consider water quantity issues. What do you think about those issues, and where do you see that those impacts being greatest?
Those impacts, we indeed included those impacts of water quality indeed on water scarcity levels. So by developing an approach that takes into account that different sectors have specific water quality requirements in addition to their water quantity demands, like for instance taking into account here the impacts of high water temperatures, for instance in terms of constraining cooling water use for power plants, or for instance high salinity levels, which may also be critical in terms of constraining water use for irrigation for certain crops. So we have indeed developed approaches for that. And what we, like you said, what we mainly see is that this has major impacts in terms of water scarcity levels, and also the population affected by water scarcity in the world. So that increases indeed from 30% if we would only account for water quantity, to 40% of the world population if we account for both water quantity and water quality issues, in terms of the population that is under severe water scarcity. And we see actually those impacts are overall largest mainly in the water scarcity hotspots in the world. So there we see that water quality is in particular important to consider. And that is like in Eastern China, for instance, large parts of India. And so there we see that those excessive water uses do not only contribute to water scarcity due to the large water withdrawals, but also due to the water that's being used and that is discharged without any treatment, that also contributes to distinct water quality issues, water pollution downstream. And that is particularly the case in regions with limited wastewater treatment. So in our water scarcity approach, we also account for that. So for the impacts of wastewater treatment, and also treated wastewater reuse and impacts of desalination. So those are all incorporated into our calculations of water scarcity.
I really enjoyed, I first became aware of your work, Michelle, when you looked at water temperature impacts on power generation and thermoelectric cooling, and from 2012, and then building on that in other papers in 2016. So there's a lot of discussion these days about energy transitions and, you know, what we should do. And I think I'm not sure that I'm hearing that much about climate impacts on different energy transitions. So paper in 2016 where you emphasized that 98% of our electricity generation at that time was either hydropower or required thermoelectric cooling. So it could be fossil fuel, coal, natural gas, or nuclear that required thermoelectric cooling. So maybe you can describe that a little bit, Michelle.
Yeah, sure. We did indeed some studies exploring the vulnerability of the power sector to climate change and changes in water resources. And so in terms of water availability, in terms of river discharge, but also in terms of the water temperatures. And so we account for impacts of climate change also on water temperature rises. And we studied those impacts for about 1,400 thermoelectric power plants in the world, in terms of cooling water use constraints and usable plant capacities. And we also looked into the impacts of changes in water availability under climate change on hydropower generation for more than 24,000 hydropower plants in the world. So we did that also by using as basis global hydrological modeling and a water temperature model. And we also developed a thermoelectric power and hydropower production model, and that was coupled to this, and used detailed information of these power plants in terms of thermoelectric power. We used, for instance, information about the cooling system type, the technology, the installed capacity, the efficiency of the plant, because that has huge impacts also on the cooling water demands. And so that we found that, particularly power plants with one-screw cooling systems showed strong impacts in terms of climate change and changes in river flow and water temperature rises. Those showed overall stronger impacts than power plants that use recirculation cooling systems with wet cooling towers. We also found in terms of the technology that particularly nuclear power plants are quite vulnerable to climate change, also because of their high cooling water demands. And so that's indeed important to take into account in terms of the whole energy transition. And we saw that, for instance, also that during recent warm and dry summers, for instance, Europe, we saw that the nuclear power plants were actually the first ones who came in trouble in terms of constraints in cooling water use and reductions in usable plant capacities. So that's also important to take into account. And in terms of our results, so globally, for thermoelectric power, we found that climate change may result in constraints for more than 80% of the thermoelectric power plants in the world, and not only due to the changes in water availability, but mainly due to the water temperature rises. And so that can result in substantial reductions in thermoelectric power plant capacities. But also as part of that study, we also looked into adaptation options, for instance, also changes in cooling system types. Like I mentioned, a switch from one-screw cooling to recirculation cooling systems could already have a positive impact here, or switching even to dry air cooling systems. And so we also tested different kind of adaptation options also in order they could compensate for these negative impacts of climate change and changes in water resources.
Right. And in that work also, you mentioned like 70 to 80% impact on thermoelectric power plant capacity, but also maybe up to 70% impact on hydropower capacity. And so these are important things to consider. When we had an extreme drought in 2011 in Texas, we were wondering why we didn't have any brownouts or blackouts, because it was extreme drought. And with power plants and electricity generation, you really don't have very much storage. So the supply of electricity needs to meet the demand at the time that you have the highest demand. And for Texas, that's, a few hours per day in mid-August when we have the highest temperatures and we have the highest air conditioning demand. And so that's when we oftentimes have problems. Of course, we've had problems recently with freezing and stuff. But so when we looked at individual plants then, and you mentioned adaptation, we found that each of them that we thought where the reservoirs were dropped and they were relying on recirculating ponds or once through cooling, that they had backup systems. And so they were able to manage and get through the drought. And so that's important. But of course, that costs more to have those backup systems. Also in the US, you know, we're looking at the Colorado River Basin and those large reservoirs, Powell and Meade, and declining storage, and the potential impact of that. If they drop below a certain level, they won't be able to provide hydropower. So increasing temperatures, increasing evaporation, and reducing water availability for hydropower. So it's a very complex system, and I admire, you know, the detailed work that you do, because there are all these cooling systems involved, and fuel sources and generation issues, and so it's not easy to try to figure out how to deal with it. But
thank you.
But there are adaptation strategies that you mentioned, you know, that they could adapt. And so in the US, oftentimes you read, well, you know, thermoelectric power plants, 40% of the water withdrawal. And then they fail to mention that, well, 98% of that probably goes back to the source system, like the rivers or whatever, at a probably elevated temperature. So water consumption, so water withdrawal, you need to have the water there for once through cooling. But water consumption, then, you know, you lose that water to the atmosphere, and it's you know, final water use. But so people are talking a lot about increasing nuclear power in France during energy transition. And I think in the 2003 drought, the nuclear power generation, the capacity was reduced to half during that extreme drought in France. So can you explain a little bit? I mean, one thing is, you know, the temperature of the water that you bring in and having it low enough to cool the power plant, but there are also regulations on the temperature that you can discharge from the power plants and its impacts on the ecosystems in the river systems. Can you explain a little bit about those two factors?
Yes, sure. Yeah, those are indeed relevant to mention. Indeed, the environmental limits in terms of cooling water use. And you mentioned indeed that severe event of 2003, this European drought and heat wave, that indeed had major impacts on large parts of the energy sector in Europe, including indeed France, but also, actually quite a number of summers have followed in which we found major impacts, particularly for the nuclear power plants, and not only in France, but also in other European countries, this was the case. Also, last summer, this was the case, for instance. And then it was actually also discussed in terms of whether certain limits would be made temporarily more flexible in order to allow that sufficient electricity is being produced. So that is really that we are then facing a sort of trade-off between these environmental limits and environmental targets that we have, but also in terms of keeping the power plants working still at sufficient capacity to ensure energy security. And so that's particularly important in countries which strongly rely on nuclear power. So that's indeed an interesting question that you pose in terms of because indeed the vulnerability of those plants they are sensitive to water availability, to water temperatures, but they are indeed also sensitive to the environmental limits in terms of the maximum water temperature, and also the difference in water temperature between the inlet and also the temperature of the water after it has been discharged, the warm water has been discharged back to the source.
So these are important trade-offs to consider, and in your adaptation strategies, then I think we have seen in the US when we shift from coal to natural gas, a lot of the natural gas power plants use recirculating cooling systems rather than once through, and so that can greatly reduce water withdrawals, but slightly increase the water consumption. But so you're not so dependent on having that surface flow. Then you may evaporate more water, but you're not dependent on having that large water flow or run through systems. But you also mentioned, we could disconnect the power generation from these water issues by having dry cooling. But there is an energy penalty associated with that. And so then you would increase greenhouse gas emissions or what, So I think maybe countries like Australia, they have a lot of dry cooling systems for their power generation. But I'm not sure that you can use dry cooling for nuclear plants or...
No, it's commonly considered as dissolution, but indeed, there are quite some advantages also in terms of using dry cooling. And you mentioned indeed quite some trade-offs that we need to consider. So you're fully right about this. And this is actually also a topic that we want to further study also as part of a new project in my group that started actually only a few months ago, which will run also in the coming 5 years. So there we also really want to look at those trade-offs between indeed water security, energy security under present and future droughts and heat waves, but indeed also what does this mean in terms of the emission of greenhouse gases. So some options, like for instance also coming up with another aspect, but for instance, we see that quite some of these options may have negative side effects, like for instance, and switch to nuclear power would be positive from a climate action perspective in terms of reducing greenhouse gases, but it may, for instance, increase water use. And the same is, for instance, also in terms of carbon capture and storage. That would, of course, be also a positive development in terms of reducing greenhouse gas emissions. But also quite some studies have shown already that this may also increase water use and may contribute to higher water scarcity. So also as part of this project, so that is funded by an ERC grant, so grant from the European Research Council, we also aim to further look at those interactions.
Right. Everything requires trade-offs. There's no free lunch.
No, exactly.
And we need to consider the trade space, what we're trading one thing for another. And that's really cool that you guys are doing a study then on looking at water and energy together. And you've been doing that for much of your research in the past, and I really like that. Another aspect of your work that I really appreciate is your work on solutions, and you mentioned already, wastewater reuse, and your colleague Jones and his papers on wastewater reuse, and also desal. And I like that you put those numbers in global context. So what volume of water we are collecting, wastewater that we're collecting, that we are treating, and that we are intentionally reusing. So it puts it in a global context. But also, even if the numbers don't add up hugely in terms of a global context, it may be an important part of a local portfolio to try to have a diverse water source, and wastewater is maybe independent, would actually increase with population growth and be independent of or less dependent on droughts. And so there are different trade-offs there also. So the global numbers, I guess, 360 cubic kilometers, and for Americans, a cubic kilometer is similar to million acre feet, 1.2 cubic kilometers per million acre foot. These are volumes that we often think of. So wastewater production, that's from municipal and industrial sources. And your work suggests that 63% of that is collected, and about half of the water that's collected then is treated. And then, about 40 cubic kilometers is intentionally reused. So these are very nice to have these numbers. I know it's a career to get the data and work up the information, but I commend you guys on doing this, so it puts it in a global context. Maybe you can comment on some of that work, Michelle.
Yeah, sure. Yeah, so in my group, and indeed also as part of this PhD project of Edward Jones, we worked indeed on the development of this high-resolution data set of wastewater production, collection, treatment, and reuse. And so we provide this on a grid-based level at 10-kilometer grid resolution, so 5 arc minutes. And yeah, what we actually did was that we combined here different global data sets, mostly country-level data. And we developed a downscaling procedure. So it's actually a model assisted downscaling procedure on these reported data. And we, in the next step, also validated our downscaled results against local specific estimates. And indeed, you mentioned already the main numbers, indeed, that we've found 360 cubic kilometers of wastewater that's being produced for municipal industrial sources. And indeed, we finally found that about 48% of that global wastewater that is being produced is released to the environment untreated, which is actually lower than what was previously estimated, which was 80%. And next to these wastewater data sets, we also looked at desalination data. And so actually both treated wastewater reuse, but also desalination are considered as key options towards water scarcity alleviation. And so there we also worked with data of about 16,000 desalination plants also in the world, and looked at the information about the capacities, technologies, feed water type, and the intended uses. And also made those calculations in terms of the amount of desalinated water that is being produced. And so we quantified that this is 95 million cubic meters per day in terms of desalinated water that is produced globally. And what is also important to mention here is that desalination, that there's also always a hypersaline rest product, which is called the brine. And we also quantify that 142 million cubic meters per day of brine is being produced. And in most countries, brine is actually also disposed without any additional treatment, and which may also have quite some negative environmental impacts. So indeed, treated wastewater reuse, desalination, they are considered as key options towards water scarcity alleviation, but there are also quite some side effects, like in terms of this brine that is being produced, but also in terms of their huge energy demands. And so, and therefore also as part of a new project that I just mentioned, which is funded by this ERC grant, we also look into the energy demands also in terms of providing clean water and water scarcity alleviation.
Right. And so considering the wastewater reuse, I think you find that the treatment of wastewater is lowest in Latin American and Caribbean and South Asian countries. And then the intentional reuse of treated wastewater is highest in the countries like Kuwait and Qatar, where they're reusing more than 80% of the produced wastewater. And of course, that emphasizes, the energy requirements to do this. And so these energy-rich countries that are water scarce, then wastewater reuse is an important part of their water management strategy. And I guess similarly with the desalination, and putting the desalination numbers in the same context as the wastewater, I guess, you mentioned 40 cubic kilometers intentionally reused wastewater, and about at an annual scale, that would be there's about 35 cubic kilometers per year of seawater desalination ongoing, and out of that is, I guess, seawater desalination.
Most is seawater desalination, but there's actually also quite some desalination of inland water resources. So that's quite important to consider. So considering brackish groundwater, for instance. So it's but you're right that the majority is seawater desalination.
Right, and then the concentrate that's generated, so with the 35 cubic kilometers seawater desal per year, then you generate 52 cubic kilometers per year of concentrate that needs to be disposed of, and that's a bit problematic. I was talking to a colleague recently from Israel, and 80% of their water is now desalinated seawater, and they're moving the discharge pipes further offshore to discharge the concentrate, and that's, you know, for environmental purposes, but also to move it away from the inlet water, so that you're not just you know, getting the concentrate into your inlet pipes and stuff. So I think they're it's both a practical issue for the desalination process, but also the energy demands for desalination, because a lot of it is seawater desal. Then they can use seawater to cool the power plants along the coast. So that's an advantage also.
Yeah, that's indeed an advantage in terms of the cooling water issues that would otherwise that I just described, which is mainly for power plants that use fresh water and that are mainly located along the river. So that you're right about that. But what is quite important is that that the energy is provided in a sustainable way. So we see quite some of these countries that in terms of the emission of greenhouse gases, that's quite some major steps need to be made to provide the energy resources for desalination in a sustainable way.
Right, and I know in Israel they've been shifting from coal to natural gas, and so that helps with reducing greenhouse gases and with their offshore natural gas, and but continual improvement would be required. So it's really interesting to see how your research has evolved over time. I mean, your early work focused on temperature and power and energy, electricity generation and vulnerability there, and then expanded then to consider water quality issues, and that you're using new tools all the time, you know, not just relying on process-based modeling, which is very important to understand the processes, but also data analytics and machine learning so that we can improve the databases. I really like your emphasis on existing data also. You know, it's not just all modeling for the future. You're looking at what has been going on over the past couple of decades. And I know it's difficult to compile these global data sets and try to use them and put them in context. So that's great. And then, you know, not just focusing on the problems, but also the potential solutions and considering the trade-offs. So I guess I would ask Michelle, what are your thoughts about the future for water resources within the context of climate extremes, change, and the linkages with water, energy, and those sorts of issues? Are you hopeful that you know, we will continue to adapt and improve, or what are your thoughts?
Yeah, I am hopeful, but I think there are definitely urgent actions needed there, and like we discussed already in terms of the water quality issues that we are facing, and that we know that climate change and increases in extremes like droughts, heat waves, floods. That may also pose additional challenges, and not only in terms of managing our water resources quantity, but also in terms of water quality. And so I think that is important, that there is really urgency there to come up with measures and not focus only on the technological solutions here, but also really focus more on emission reduction measures. I think that is quite important, that we work on this as soon as possible. Because indeed, water quality matters indeed, not like we discussed already for water scarcity, but actually also in studying the whole nexus of water, food, energy, and ecosystems, as it is. It's really a cross-sectoral issue. Sectors depend on water, but they pollute the water also during its use. So there are two-sided interactions. And I think that's quite important, that we better understand the drivers of these issues, also to come up with an adequate set of solutions also. So that is also what we really aim to focus on, and that I hope to focus on also in my group, but of course also together with colleagues from other institutes, that we can join forces, and that we can help to reduce these knowledge gaps, and provide the relevant knowledge and information to better support and further improve water management and decision making here.
Yeah, I think, you mentioned that you're working with the World Bank and other groups, and that's wonderful. And your modeling approaches allow you to isolate and attribute, to conduct the attribution analysis. So who's causing the water quality issues? And that's essential if you're going to develop appropriate solutions then to understand the causes. So what I like about your work, also really admire, is that you look at the past and you look at the temporal evolution over the past couple of decades, and then you project forward then with the climate change and socioeconomic impacts. So it's a quite complicated system and pretty nuanced sometimes, and requires a very detailed understanding. But I appreciate that your group is trying to fill data gaps and put things at a global context with the numbers and then also the modeling analysis. So thank you so much, Michelle, for joining our Water Resources podcast. Our guest today is Michelle Van Vliet, and I will highlight many of her work on the website, so you'll be able to access the papers. And Michelle is at the Department of Physical Geography at Utrecht University. Thank you very much.
Yeah, thank you very much, Bridget.